Hi everyone. So in this video, I'm going to go over that whiteboard exercise you were all thinking about. Okay, so just to recap, what we have here is the following wave function. It's an upside down parabola between 0 and L. And what we're asked to do is to find the expectation value of momentum squared, the uncertainty in the momentum, and then also to think about what this might have to do with the Heisenberg uncertainty principle. Okay, so let's dive right in. So to find the expectation value of p sub x squared, what we need to do is the following. We need to apply our momentum operator twice, so we have our psi star of x here. Our momentum operator twice gives us two factors of minus I h bar, and then we have a second derivative, d squared psi of x, dx squared. The whole thing is iterated, dx. Okay. Now, because the wave function is only non-zero between 0 and L, the bounds of integration here we're going to change to 0 to L when we start integrating. So let me note that. So bounds 0 to L. Also, this piece, this is minus I squared. This turns into I squared h bar squared, or minus h bar squared. And also, since this wave function is purely real, psi star is equal naturally to psi. All right, so what we got to do first is to take derivatives of this. So let's take derivatives. So we have d psi dx equals they're not really partial derivatives here, so I'm being a little sloppy, so we have to differentiate this. I gave you the normalizing constant to save you a little bit of work. So the constant here can get pulled out, and so that gives me 30L5 to alpha root L to the fifth. Then either you can use the product rule, or you can multiply the whole thing out, whichever you prefer. I'll multiply out here. So this gives me Lx minus x squared. If I differentiate that, I have a constant, and then I have derivative of Lx is L, and then minus x squared pulls down a minus 2x. Okay. What I need is the second derivative, so if I have d squared psi dx squared is going to be the derivative of this, right? d dx. Now we have our constant again, and our L minus 2x. Well, the first term with L is just a constant, so that's going to vanish. And then differentiating all of this is going to give me a factor of minus 2. So I end up with minus 2 over root 30 divided by L to the fifth for my second derivative. So this means I can put that back in over to here, plug that in, and this now leaves me with the expectation value of p x squared. Now I'll be careful about putting my limit in. So we have, I'll pull out my minus h bar squared from the middle here. So I have a minus h bar squared, integral 0 to L, now of psi star, which is really psi, so that gives me a 30 over L to the fifth, x, L minus x, times this piece here, which gives me a minus 2, and another factor of root 30 over L to the fifth dx. Let's just collect up all the constants. So let's see, we have a minus 2 canceling that minus sign here. Then I'll pull out all the 30 over L to the fifth. So we have 2h bar squared times the quantity 30 over L to the fifth. And then we have just this part inside. I'll multiply out again. Integral from 0 to L of Lx minus x squared dx. Now this is a polynomial, so we can integrate that straight away. I'll simplify the outside here. 2 times 30 gives me a 60 h bar squared over L to the fifth. This term integrates, so to Lx squared over 2. I have a minus x cubed over 3 here, and this is evaluated from 0 to L. The lower end point gives me nothing. I just have to plug L in here. So I get 60 h bar squared over L to the fifth times L cubed over 2 minus L cubed over 3. And that ends up being 1/6 L cubed. So I have 60 over h bar squared divided by L to the fifth times L cubed over 6. And so just to finish this off on the same page here, I end up with P expectation value of P sub x squared equaling 10 h bar squared all over L squared. Okay. So now our next thing is to go and calculate the uncertainty in px. Okay. So sorry about the background. We've got a little bit of dinner being cooked by my wife in the background. Smells amazing. We do trade off the cooking, yeah, but we're both fortunate to be reasonably good at it, I think. Anyway, so now our goal is to find the uncertainty in momentum delta p sub x. We know the expectation value of px is 0 since my wave function is real. We talked about that in class. So, using that theorem for the variance, what we have is that the variance, the uncertainty in p of x squared is equal to expectation value of px squared minus expectation value of px quantity squared, but that goes to 0. So I just need to square root this. So delta px equals the square root of px squared in this case. So we end up with, if I use the result we just had, we have square root of 10 h bar squared over L squared, or simplifying, this leads to the uncertainty in momentum being, I have an h bar and an L times the square root of 10. Okay. So now let's think about what this means for the Heisenberg uncertainty principle. So notice that, right, delta px goes like 1 over L. So if we increase L, right, we decrease delta p of x. This should make sense because, right, so the uncertainty in x, right, if we look at just from staring at the shape of the wave function here, right, it's not gonna be L, but it's gonna be of the same order of magnitude as L, is of order L, And the Heisenberg uncertainty principle, so which I'll abbreviate AQP, requires delta x, delta px greater than or equal to h bar over 2. So if we increase x, that means we're increasing our uncertainty in x. We better well be decreasing the uncertainty. It makes sense that we're decreasing the uncertainty in px, which is exactly what's happening. And so this is consistent. Like, and conversely, if we make L smaller, so we decrease the uncertainty in x, we're going to increase the momentum uncertainty. Now, what I didn't ask you to do it, but a detailed calculation shows that the uncertainty in x in this case happens to be L over 2 root 7. So for this wave function, the product delta x delta px happens then to be L over 2 root 7 times h bar over L times root 10, or canceling out my L's, I end up with h bar over 2 times the square root of 10^7. So this is, in fact, consistent with the Heisenberg uncertainty principle, but the product of my uncertainties is larger than h bar over 2 by whatever that's going to be a little bit more than 1, this square root factor here. So that all checks out, and we can see that the Heisenberg uncertainty principle works in this case, and we've seen how one can calculate the uncertainty and momentum for a given wave function. Thank you.